Okay, so first of all, thank you everyone for coming to this reading group on deep generative models. We are going to go through the deep generative models, some foundations, and especially a unified view of deep generative models using a lot of the knowledge from previous lectures, such as variational inference. And then we'll go to some applications, including some tricks and some interesting examples, some very promising future directions, such as integrating domain knowledge into deep learning. First of all, this lecture is it's about unifying the theoretical perspectives of deep generative models. The reason why we are interested in this topic is pretty clear. First of all, this is the trending topic. Most recent year, many recent year research works, especially in the CV domain or so, they are using the generative models. And also, it could be applied to so many different tasks. And so this is the reason, basically the reason why we are interested in deep generative models. And to start with, we first define what is a deep generative model. And deep generative model, the word deep basically refer to that we have multiple layers of hidden variables. And generative model is just the concept that most of us should have already known. It's like interested in a distribution and instead of just boundaries, and to predict px, y versus just py conditioned on x. Yeah, those are the basic concepts. And the course materials we based on is Professor Eric Xing's lecture 12 and 13. And there's a very important prerequisite on the variational inferences, which was previously presented in our reading group by Yewen, especially lecture 7. And if you have any question on the technical part, I think it is a good idea to revisit that lecture. Okay. And let's get started on some early stages of the deep generative, not really, yeah, of the deep generative model, some early forms. And as you can see here, this work is published in 1992. That's pretty early. And oh, by the way, I have made most of the references and URL link. If you go find my slides, and you can find it, you can just click it and go to the paper. And so sigmoid belief network is a very popular early form of the deep generative models, where this is a hierarchical Bayesian model, where we link the layers via the sigmoid functions. And yeah, and like we pass multiple layers of the hidden variables, and then finally we have a visible layer. It's this kind of model. And there are other models such as the Helmholtz machine, and this machine is somewhat similar with what we have as a deep generative model framework in mind. It has it has the design of unifying an inference and a generative process, and to run a generative model on the input X, and also run the inference model on the hidden values. It is using the process instead of a mass expression to define the model. And the inference and the generative models, they can be they can be related, and but the two models can be totally different as well. And if we write it down like this, it's like the nth layer and the n-1 layer of the network. The formula seems really similar with something like the like a like a cyclogram or something like this. The idea is a bit um, similar. And another work that we mentioned is this predictability minimization. And this one, it's a series of work done by, sorry, I am not good at pronouncing his name, Skimberg, and since 1991. And there's a lot of work published since then. And also there's a conclusion on arXiv. And this work, it defines a training procedure, not really a model in a rigorous way. And there are it is using alternative loss functions containing an encoder network and a predictor network. And it uses the training procedure instead of a global mass expression to define the model. And yeah, it's the idea. If someone is familiar with the generative adversarial nets framework before, it's like the idea is pretty similar. And in fact, Professor Xing mentioned in his lecture that there are debates going on, like about who is the first one to come up with the idea about the generative adversarial networks, like the modern time generative adversarial networks this way. And the conclusion the link I put here is it's a summary written by the author himself. And I think he is trying to claim that the generative adversarial networks basically inherits the idea of this predictability minimization. And in recent years, there's a resurgence of deep generative models. And just for example, the deep belief networks, it infers it influencing okay, and this is this is a belief network that is in the a deep learning framework. And this is a hybrid graphical model, and some layers are somewhat directed and some layers are undirected. And this link is also clickable. And we can, and something that is mentioned in the lecture is saying that inference is problematic due to a phenomenon called explaining away. And according to some of the information I found online, it's like the explaining away phenomenon is saying that if we see an observation A and there are two potential causes like B and C, then when we see A happens, then the chance of B happens and the chance of C happens both become higher. But if once we pick one cause, like we say for sure that this time A is caused by B, then the chance of C goes back down. This kind of thing. Yeah, and also some other models like the Boltzmann machine, which is a deep undirected graph, and variational autoencoders, which we will go into more details later. And it's or like the neural variational inference and learning, and that both of them are somehow based on the variational inference idea that we talked before. And the yeah, and it's the first modern actively used deep generative model. And it's basically regarded as old ideas, but has very excellent executions. and so produces nice results. And the two parts of the model, which I mean the two models means the generative and the inference models, those models can be very different. And this model is generally trained in a variational way that we are going to talk about soon. And of course, there comes very like one of the most popular models, um, deep generative models nowadays is the GAN model, generative adversarial network, which goes like this. We have a discriminator try to tell the difference between real data and synthetic data, and the synthetic data is generated by a generative model from some noise distribution. And it has some countless ideas following it, like all those generative model ideas. Um, and we have a zoo of such models, so that I'm just listing a few examples here. Yeah, and again, like the model we refer to is later on in this lecture, we can just say that the model that we are talking about are mostly not just a model. It's for example, in the generative adversarial network case, we are defining a procedure. And there are some synonyms in the literature that most of us might have already come across. It's like, for example, we say the posterior distribution, and or like an inference model, and they have other names like variational approximation, recognition model, inference network, recognition network, or just a probabilistic encoder. Like the model that we are saying, we're talking about, it's or like most likely refer to the generative model itself, or like we can call it a likelihood model, a generative network, a generator, or maybe a decoder. And something more about training. It's like the training of the early forms of the deep generative models typically uses some EM style framework. The first way, like we're going to talk about three ways of doing this. The first way is to do it via sampling and data augmentation. It's like directly infer the hidden variables given the observation. And the second way is by variational inference. It's the generator, have the generator parameter theta and variational inference model parameter phi, and optimizing a variational lower bound, which means that it's the loss is the lower bound, and we try to maximize the lower bound of it. And there's also an wake sleep algorithm. It's a loss function um, defined in like two similar but not really the same way. It's like one is the wake phase, one is the sleep phase. In the wake phase, we try to optimize the generator, and in the sleep phase, we try to inference phi, like the other part of the model. And an illustration that was drawn by Professor Xing in his class, like he was just draw it by hand on the slides, but I try to like make it like, I think this is a very good illustration, so I put it here. It's like the difference between among the three methods. It's like the data augmentation directly go on optimizing data, and variational inference is trying to like somehow using the two um, the two variables, like try to optimize them one by one, and trying to go to the maximum point. But the wake sleep algorithm is somewhat like using two slightly different, but not that different objectives, and they could be optimized really in a different way. And actually, there is not um, a very it's never guaranteed for sure that they will finally agree with each other, but most likely we manage to make them agree with each other in the end. Yeah, and also a quick review on some very important ideas, like the variational inference. It's it's a variational, the fancy name of optimization. And variational inference is studying the inference problems while an optimizational tricks. And the challenge is that the directly infer the distribution P might be arbitrarily difficult and often intractable in practice. And so that we need to introduce some other distributions, for example, Q, that is generally tractable. And then we expect P and Q to be close to each other, and we can perform variational inference on them. It's like, well, we're basically using Q to help us to put the problem into an optimization method. And a very convenient choice of measuring this, like how far it is from distribution P to Q, is a KL divergence. And like this, it's like we consider a generative model P theta that's generating X from Z and the prior Z, and we have the joint distribution like this. And assuming that we have a variational distribution Q that's generating D from X, and we maximize the lower bound of the log likelihood, and it's the equation that we've seen before, and the KL here refers to the KL divergence that we've just mentioned, and the KL divergence is defined this way. Yeah, and of course there are multiple ways of expressing its objectives. It's variational inference. It's not the only way of expressing the objectives. And something more on the KL divergence. The KL divergence, it's like because a bit more on knowing a bit more on it will help us feel better using it. And so first of all, it's good to have the intuition that KL divergence is not like KL divergence of Q on P is not the same as P on Q, and it's asymmetric, and this property is useful later on. And also it could be written in other ways, like it could be written as the difference between an entropy and a expectation of the log of the log of px. Yeah. And maximizing the variational lower bound. In most of the cases, it requires two steps. The AM style algorithm, it requires an A step and an M step, and we can do the same thing here. It's like we can optimize on phi in the E step, and optimize on theta in M step. And also this is like maximizing this L is the same as minimizing this F, which is completely just reversed it. And this F is called the free energy. And here we are calling it an E step and an M step, but this is maybe not the very accurate naming. And according to Professor Xing, it's like in a way both steps are somewhat M steps, but just using this EMs, this expression to refer to that this is an EM style framework. Okay, and something that we are going to be is going to be useful to us soon is the log derivative trick, and just a quick recap on it. It's like so when we have a expectation of Q on P, and we want to take its derivative, and where theta is only has something to do with P, not Q, and then we can try to, like, first of all we can put the derivative inside, and then we somewhat like through from this step to this step, and it's just times p theta divided by p theta, and then we and then from this part, like as like nabla p divided by p is turned into a nabla log p, and this transformation is called a log derivative trick, and it's often used when we deriving an expectation over a distribution. And the reason why we can't stop in the middle is because the nabla p itself is not in general a valid probability distribution, so we can't just directly use this to estimate the value of it. And the log derivative trick on its own, it's just very simple math behind it, just the simple derivative rule plus some chain rule, and it could be used to simplify the calculation of a nabla p, because of like we can do a simple transformation, like put in this one here, right? So this is just some explanations on the log derivative trick that we'll see where we use it soon. And for the wake, or something more on the wake sleep algorithm, and the wake phase, and basically we try to minimize the expectation of the log of p over q, and maximizing the variational lower bound of the log likelihood, or like minimizing the free energy like this, and it's corresponding to the variational M step, and it gets the samples from the Q theta Z over X through inference on hidden variables. And the sleep phase, it's becoming a little bit more complex than the wake phase. And this is simplified as minimizing the over the joint distribution of X state on of the p theta joint distribution, and then we we apply the log derivative trick here, and finally and finally it's like yeah, and finally we can estimate the value by Monte Carlo algorithm. And the and it's like we actually uses a different objective, which is called a reversed KLD with respect to phi, to is the optimization, and let's call it F. Yeah, it's this reversed KLD here. The part that is changed is this part, the KL, and this step generally corresponds to the variational E step. And the reason why we change the objective is because the original objective function is suffering from high variance caused by the gradient of the original KL term. And it's generally intractable. It's like, so by changing it this way, it's like the new objective is somewhat making us dreaming up samples from dreaming up the generated samples, the synthetic samples through a top-down path. This reversed KLD is something that is wrong, because it's like we are no longer sticking to the original objective, but it's not too wrong, so that the wake sleep algorithm still work in practice.
So Patricia, yeah, I'm not sure whether you're going to go to the detail anymore, but since I'm less familiar with this wake sleep way to do the inference, can you try to like motivate us what exactly we're doing? Because for the variational inference, we know that, okay, we're going to maximize something, but it's very difficult. So we try to find a approximate kind of lower bound, right? So we wanted to maximize the lower bound instead. And that lower bound will be computed based on some KL divergence and do some rearrangement, and then we can get that elbow, that lower bound. So for the wake sleep, can you also try to motivate us? What's the intuition behind this kind of inference?
Okay, so basically, this intuition is it's very similar, like as I put here, very similar to the variational inference. Like we've been talking about, the M step is somewhat correspond to the wake step, and E step correspond to the sleep phase, and mostly the wake and the M step, they are identical to each other. They're optimizing exactly the same thing. And of course, the general the goal, it's oh, sorry, I think I should put I should put P here. The P theta is, oh no, Q5, yes, okay. So here it's like the M step we put here. Basically, okay, so M step and the wake phase, they are the same, but the difference lies in the E step and the sleep phase. It's the different ways of trying to handle this phase. It's like in the variational inference E step, we are trying to optimize exactly the same objective as it is in the M step, and suffer from high variance, and somewhat need to do the variance reduce in practice. And but we learn with the real samples of X. And in the wake sleep algorithm, it designed it to be, it's like somewhat switching the two parts, the KL divergence calculation. It's switching. It's putting Q's by here, where it was measuring KL divergence from Q to P, but this time it changed to from P to Q. And this change is what we just called a reversed KL divergence. And so that this time we are measuring something different, and which has a lower variance, and learn with generated samples of X in the sleep phase. And in the wake sleep algorithm, we use two objectives, and in theory, it's not guaranteed to converge. And where in the variational inference, there's single objective, but it's guaranteed to converge. And of course, there are some benefits, like the low variance.
So
like this.
what do you mean by generated samples of X? How we can generate that X?
Generated samples of X is it's those we generated from P theta.
Because theta has been already optimized in that
Yes, in the other
first step. Okay.
Yeah.
Okay. And why, I think in the earlier slide, you mentioned that for the weak sleep mode, it's like optimizing theta and phi as if they are in two independent process. That if you look at the slide, the summarization slide, right? So still, it's like we're going to fix the phi to optimize theta, and then we fix theta and to optimize phi. And also the X is kind of dependent on theta, definitely, right? So there's some sort of dependence.
Yes, some sort of dependence, but having two different objectives to measure.
Okay, maybe those three illustration figures too abstract too.
Yeah, it's very abstract. It wasn't really something that's plotted in the in Professor Xing's slides. He just hand draw it, and I just copied it down. Yeah.
Okay.
It's just a very from the concept level.
Okay, and in practice, I think variational inference almost is the most widely used, right? So for the weak sleep,
yes,
I'm not sure whether you have seen that in some paper, but for me, I never see any paper really utilize this technology.
Yes, but it's like still discussed later on. It's like it's like trying to. I think part of the goal of this deep generative model, this course, this part of this course is to find some correlations between the very similar models, find some correlations and differences, try to unify those different ideas. Yeah. So this is like what we've just done is to correlate the weak sleep algorithm to the variational inference. Yeah. Okay. And now we can go into some modern time deep generative model examples. For example, the variational autoencoders, VAEs. Sorry. And the key idea is that we have a inference model like this and a generative model like this, and prior PZ and joint distribution P theta. And we use variational inference with an inference model, and we enjoy the similar applicability with the wake sleep algorithm. This is the variational autoencoders design, not really complex. Oh, and by the way, I put the paper here. It's clickable. And the variational lower bound here, we have it again. And recall that for variational inference model, we suffer from a large variance in the sleep phase, or where we call the E phase. That is because of this term. And so this time the variance is reduced via a reparameterization trick. And of course, there are other alternatives of reducing the variance, like using control variates as the reinforcement learning, and those are some many other ways. But this time it's chosen to be the reparameterization trick. And the reparameterization trick in the gradient estimation is like so first we try to assume a trivial noise distribution. For example, it could be a standard Gaussian. And this is like where we denoted as a epsilon. And then we do a deterministic transformation. We transfer the process of like sampling z from q phi z over x to the process of like z is a function of like taking phi as parameters, and also consider the noise distribution and x. And the reparameterize the expression will look like this. So instead of just a sample over this q, we take an expectation over epsilon, and then we do then we take the derivative of this part, the log of p, and yeah, x z phi, that's generated according to this noise distribution. And it has empirically lower variance of the gradient estimate. And some of the results from those paper. This is not made into a link, so it's just telling you that there's a work to generate the celebrity faces, and we can say that it's pretty blurred, and they doesn't really look like real world photos. And so this is said to be because of the mode covering behavior that we are going to talk to discuss more later when we talk about the generative adversarial nets. And the model covering behavior has something to do with the chaos divergence. I'm putting some reference I found here. Yeah. And another very popular, very modern technique is the generative adversarial nets, as we just plotted. This is exactly the same figure that we see how we use a discriminator and a generator to try to help each other train better. And the paper is here, published in 2014. And the discriminator, where we just, for convenience, just call it D. And then this one is trained first, and then the generator G, and is trained after it, and then D again, and then G again. It's like we are training everyone, like training D until convergence, training G into convergence, and through many iterations until they reach a balance. And while training D, we try to minimize this. It's like we try to, while training D, we try to tell the difference between the real data and the synthetic data. And while training G, we want to fool the discriminator. It's like we want to make the generated samples regarded as as real examples. Yeah. And in theory, there exists an equal point. There's like if we view it as a game theory problem, it's like there could be an end of this game when the generated distribution is identical to the real distribution, and the discriminator couldn't tell the difference. It's only like at any point, it only knows that there's half chance of being real or synthetic. And some of the examples from generative adversarial nets this is some work done by Redford et al. In the year 2016, and they are the generated bedroom examples. And from those examples, Professor Xing specifically pointed out that GAN tends to generate sharp images, but they are narrow. By saying that they are narrow, it's like, for example, it's from those examples, we see that it's focusing on generating bad, or maybe sometimes include something like like sofa or something near it at the door, and it's very it's only focusing on on those on those common things. But in general, those figures are those images are very sharp. It's like not blurred anymore. We can see the clear boundary. We can see that they are like real. And next we are going to try to unify the different models into similar framework, because they doesn't look like that similar to each other. And an analogy that was mentioned in in Professor Xing's lecture is that this effort is trying to move from the alchemist to be in a modern modern chemistry work. And it's like we're trying to find some basic elements, trying to find some rules, and there's no need to like try endless times and want to find something good with luck. We can build some theory to guide us have a better practice. And there is a paper called Ununifying Deep Generative Models. And what we are going to talk about next are mostly from this paper. And it's so on a very abstract level, we say that GAN GANs are it's a play of achieving an equal point between the generator and the discriminator, and VAE is trying to maximize the lower bound of the data likelihood. And we want to make their expressions a little bit similar with each other. And we can try to, those are the works that we're going to do next. First, we'll try to see how the GAN objective could be transferred into a variational EM format. And then we can see that the VAE's objective could also be rewritten into a new format. And the linking GAN and VAE to wake sleep algorithm is also possible. So first, a GAN objective. And so here we can actually try to introduce a new label that's called Y. And this is the new form of the objective, where the Y is saying that the Y is the label of the source of this data. It's like if it's from the real data, then Y is 1. If it's synthetic data, then Y is 0. And this is how we get rid of like the expression of G theta and PPG theta and P data all the time. We try to uniform it into P theta XY, and that's it. And also there's a and also like there's a rewriting of the objectives. So previously the objective we have is the minimax game between the between theta and phi, between the discriminator and the generator, and which could be written into this, like when we are training the discriminator, we do this, and when we are training the generator, we do this, and we can rewrite it into a new form by introducing the y. That's we talked about this y. And it's a label of whether or not it's the synthetic data, and it's written this way. And here because this is the first time, so I just write it as y1 minus y. Recall that y is either 0 or 1, so it actually means that when y is 0, we expect it to be 1, and when y is 1, we expect it to be 0. So that's why it's called reversed, and that's why I put it as a reversed q phi here. We will use this expression later on, the reversed q phi. And as we can see, it's no longer two different objectives. It looks like the almost like the same one, although not exactly the same, but looks almost the same. And the only difference is a reverse.
So Patricia, will you explain why those two forms are equivalent under the new notation y?
Not really equivalent. There's still a reverse of the q phi. It's because
So we say we have a new form.
Yeah, the new form.
Yeah, the new form should be equivalent to the old conventional form, which is like the GAN framework, right?
Yes.
Yeah, so I just wonder like why the first block of two objectives actually are equivalent to the second block of optimization problems.
So I think it's because we get rid of the differences between the x getting sampled from the synthetic data or x sampled from the real data. Like we somehow use y as part of the parameter of this model, and so that it's just like rewriting it into a new form. It's like this time y is like this first part of the discriminator loss. It's where y equals 1 for always, and the second part is where y equals 0 for always.
Right.
Yeah, and when we put them together, it's like it's like we are trying to we are trying to and so we can put them together into like
yeah, when we sample x, we can
put them together. Yeah.
So for the second one, it's kind of that's the joint distribution over x and y.
Yeah.
So it's like when we try to do the sample, we need to sample together x and y. But then afterwards, how the discriminator y it can come to this q.
It's like q is the function to tell whether or not it's from the from the synthetic data, or it's from the real data. And so we are once again we're expecting the y to be to be 1 when it's the real data, and to be 0 when it's the synthetic data. So this is like, I think it's just like rewriting.
Is there any definition to this Q?
Oh, it's not. Let's see. It's not written in the given slides, but I think it's just taking the outcome of this discriminator as part of the
For the output of discriminator, it says it's going to be a probability.
yeah. The output of the discriminator should be 0 or 1.
Okay.
Yeah.
The hard version. Okay.
Yeah.
Yeah, I mean, in the high level, I kind of agree that they should be the same, but just feel like the details, it's like the exact one mapping is not that clear. Of course, like one way is like we decompose this equation into 2 components. On the right hand side, we can decompose it into 2 components, right? So then we decompose it like when y equals to 1, then we have one term, and then y equal to 0, we have another term, and then we try to do the comparison. Okay, so then how about the second line?
The second line is just it's only from the it's something that's only coming from the synthetic data, and it's like this time when we are trying to train it, we try to we want the prediction to be fooled. It's like we try to make the discriminator perform as bad as possible. So I mean, this is the reason why there needs to be a reverse choose.
So then for the original optimization problem, actually this X is purely generated from the synthetic, I mean the generator, right? So, but for the new form, we still have saying that Y, and we didn't exclude the situation where Y equals to 1.
Yes, like from the expression we didn't.
So then for the second line, what if Y equals to 1? What will happen?
We'll expect it to look like to have the result that Y is. We'll encourage it to have the result of Y is 0 as the prediction outcome.
Yeah, I think I do not quite understand why that Y equals to 1 should involved in the second line of up function. Because somehow it's like, if we go back to the original equation, right? So essentially we're saying that, okay, once this discriminator is fixed, then we try to learn the best theta, or in other words, the best generator to fool that discriminator, right? Then everything is quite natural. But then coming to the new form, the second line, because it tries to unify everything, right? So it definitely has combined the 2 cases together. For the first one, indeed, we need to consider both cases, so the problem is less severe. But for the second line, I just wonder how Y equals 1 is gone or not affect the optimization problem.
I think it's like, to my understanding, it's probably just the way that people express it, because like, for example, in the conventional this part, in this format, in this old form, we can actually add this at the alpha's first term into the L theta, but it doesn't affect the outcome at all. It's like, yeah, because actually we are maximum doing minimax game on the same objective, but the reason why we only need to keep the second part is just because we are actually interested, not really interested. It's like because we are only optimizing phi. No, not phi. No, we are only optimizing theta this time, and theta is not involved in the first part. So it's like adding the first part in. It's almost like
I see.
adding
So this p theta x given y when y equals to 1, actually it will not involve theta at all, right?
Yes, it would.
It will be p theta x. So can you please go back to the previous slide? I see. Okay.
Yes.
Okay, I think it's clear to me now.
Yeah.
Okay.
So
Thank you.
It's in a way just how we write it, how we write it down. And I think this new form should look a bit familiar to us, like in the previous slides, that those forms of like either the wake sleep algorithm or like the variational inference, and all those EM framework that we've gone through. It's something that's pretty similar with what we have here for the new form. And that is like, we can show that, yes, they are pretty similar, and they can be like, okay, so we can try to transform, not transform, we can try to express the GAN in a variational EM format. And let's see the variational EM where we have this loss function, and we try to maximize theta, maximize phi over phi in two different phases, but we have a single objective. And in a GAN model, although we already write it this way, we still have two objectives, although they are pretty similar to each other. And something good is that we have similar components, like the generative model and inference model. But something different is that something kind of tricky is that in the variational EM, we used to use p theta to name the generative model, and here we kind of here it actually interpret the q phi as the generative model, and the p theta as the inference model. And the reconstruction term here is similar. This term, the expectation of log p over q, and it's similar to the GAN's objectives. And there doesn't exist prior regularization of PZ. This is the special case of, and it's not the special case. It's a big difference between the GANs and the variational EM, because in the variational EM we assume a prior like regularization on the distribution of Z, but here there's no such things. And so we find some correlations, like they are somewhat very similar, but they are also a bit different. Like, for example, there's still two objectives, although one of them is only like reverse of another. And minimizing, and also we can say that we can use the we can use the minimizing KL divergence. We can use this point of view to see the GAN model. And traditionally, we have the maximizing the maximize the variational lower bound. We have seen that we can do this. We can maximize this bound, and which is equivalent with minimizing the KL divergence, not fully equivalent to, I mean, involving minimizing the KL divergence for the inference model to the posterior. It's this term. And here, this equation here, down here, it's the derivative of this equation. It's given in lecture as a lemma, and didn't prove it. And it's okay. So first, starting from an initial point where we call the theta 0, phi 0, it's the starting point of how the parameters looks like. And we have a py be a uniform prior distribution, and like y, the thing that we mentioned before, the y is just the where the data comes from. It's from either the synthetic data or the real data. And here this lemma just call that just say that if we do this computation on the reversed Q, and this is the outcome we have, the difference between an expectation on KL divergence of P over Q and Q reverse, and JSD. And JSD is what we call a Jason-Shannon divergence, different from KL divergence. This one is how to say? It's symmetric, which means that like if we switch the two parts, it doesn't affect the outcome. And I kind of believe that maybe the more details should be found in the related papers. It's just in the course that it's just given as for granted. And yeah, it's exactly the same lemma on updating rule for the theta. And the connection to a variational inference is here. If we see x as a latent variable and y as visible, and p theta equals to p when theta equals to theta 0 x, and this is a prior distribution, and q reversed, and inferring y, inferring x from y, it's like an S posterior distribution, and p theta as a variational distribution. Then this is said to be pretty similar with the variational inference. And also, okay, so this one is just the exactly that slide from Professor Xing's lecture. I pasted here because this is a very interesting illustration, and to try to explain the reason why GAN generate images that are sharp but narrow. So here it's like the GANs, when we are minimizing the KL divergence, like the step that we specifically focused on, and we are doing this like as in this frame, it says that the KL is is the KL divergence is this equation, right? And so it says that the large positive contribution to the KL divergence in the regions of X space where QR is small, and it's like if this one is small, if the green one is small, then the red one will contribute too much if it's big, and then so that when the green one is small, then the red one tends to also be very small, and so the red one tends to avoid regions where the green one is small. And here I'm just using the color to name it. It's like the blue one is where the real data, it's the shape of the real data, and the green one is the is like what we expect to see about the synthetic data, and the red one is like what the what the synthetic data really looks like. And it's like and this figure is such an example. Let's say that where we get started is like we try to we try to make it close. We try to use the red one to approach the green one, and it's like, but finally what we end up with is that we're missing some of those, we can say that missing some of those features that are not that popped up. We are only capturing some of the very obvious features, and like so this, like for example this, so this part that we missed is called a missed mode, and this helps explain why in the generative adversarial nets we see the images that are sharp but but narrow. And yeah, and as an example, it's like you, like in your data set, in a GAN models training data set, if you put in some noise images, it wouldn't easily affect the outcome unless there are many of that kind of noise. And also we can write a VAE into a new formulation. VAE here, we traditionally maximize the variational lower bound like this, and we also introduce the real fake indicator Y and an adversarial discriminator. And also beside that, we introduced a perfect discriminator Q star, where the Q star tells that Y equals to 1 when X is real, and Y equals to 0 when X is generated. And Q star is introduced this way as a perfect discriminator. And also a generative distribution, instead of being only an X over Z, it's like X over Z and Y. And but depending on different Y values, it's once again, it's like if Y is equal to 1, which means that this is the real data, we only sample from the real data. And otherwise we do it, we generate the X from Z. And this equation is also given as a lemma. It's like the new objective of VAE still at the point of theta 0, phi 0. And of course, there's a very obvious posterior, like we can see that this is proportional to, and this is what how we define it to be. And yeah, and this is the equation of new objective. And here, what is important to notice is a part of the KL divergence that we write here, the KL, this part, and the KL divergence to minimize for the VAE is this equation. And recall that in the new format of GAN, the KL divergence to minimize this term is the P theta and over the Q reversed X, Y. And so in a way, we can see that they are actually, although they are really similar, but actually they are somewhat reversed. Like the VAE, it's the KL divergence. It tries to minimize is a KL of Q to P, and the K and for GN is from P theta to Q. And so the major difference just popped out when we try to align them to each other. And the GAN's KL term does the minimization of P theta over Q. And the VAE tries to do the minimization of theta, but it's Q over P. Oh, sorry, I missed KL here. It's like minimizing theta KL P. Yeah. And so GAN tend to miss some mode, ignoring the regions with small values of P data. But the VAE is tends to cover regions with small values of P data, but probably just covering too much of them so that sometimes the image becomes blurred. I will correct this slides after the meeting. Okay, and here's another point of view. Like we can link the VAE and also GAN to wake sleep algorithm. And the wake sleep algorithm, recall that we have this kind of distribution, and we have this kind of expectation to compute, and we try to minimize over theta or minimize over phi in wake and sleep part respectively. And the VAE objective here is like VAE is almost like only needs the wake phase. It does not really need the sleep phase, and it doesn't need the reverse KLD trick. And it always stick to minimizing the wake phase KLD, but it's with respect to both theta and phi. And the GAN case, it's, as we can see from easily compare it to the wake sleep sleuth, we can see that the GAN is quite the opposite. It's directly extending the sleep phase. Only difference is that from Q's from Q phi to Q phi reversed, and stick to minimizing the sleep phase KLD. Yeah. And so now we reach the conclusion point of the first half of this of Professor Xing's lecture on the deep generative models. And it has a long history and a big family. And unification of the different kinds of deep generative models is possible and also useful, help us explain some differences in between. And GANs and VAEs, they are biggest difference is that they are minimizing KLD in the opposite directions and extend to the two phases of the classic wake-sleep algorithm respectively. The general formulation is useful for analyzing a broader class of the existing DGMs and can help inspire the design of new models, hopefully. And when we come to the applications, and here we can see that we can say that the GAN is pretty trending these days because it is really the generative adversarial networks has very outstanding performances in the applications. And the vanilla GAN, the one that was published in 2014, its objective could be written this way. And it's like the JSD, the JS divergence that we've talked about previously. And it's data between the data and the generator generated results. But note that this expression is just symbolic. It's not executable. We can't just compute this directly. It's just the idea. Yeah. And there's an unifying version of the objective. It's to compute the KL divergence of the P theta over Q. And it's in this work just mentioned briefly. And there's so there comes some very interesting applications that pops out and worth mentioning in this class. The first one that comes out is the Wasserstein GAN, or like W-GAN. Its motivation is that we observe some shortcomings of the KLD. It's rooted in the nature of KL divergence. It's okay. I mean, we observe some shortcomings in the traditional generative adversarial nets design. It's because of the shortcoming of KL divergence. It's like in the KL divergence, if the P and Q have neglectable overlap, which means that P and Q are too different, then it becomes meaningless to evaluate the KL divergence. But in practice, this is not a very rare case. In practice, sometimes the P and Q can be really far away from each other, especially when our data is a low-dimensional manifold of a high-dimensional space. And this could happen for always. And so a fix of that is to redefine the method of measuring the distance, and which is called a Wasserstein distance. This is a well-defined distance in mass, also known as Earth mover's distance. It's Earth mover because this distance is measured by the transportation cost of making a pile of dirt from one shape into another. It's like if we see the distributions as piles of dirt, like how to make this pile into that pile. It's this kind of distance. And I'm putting this this page here because of the nice illustration of this figure. And the Wasserstein gain, it's defined by this objective. And here, what's involved here is a Lipschitz continuous. And this continuous, I think we've mentioned multiple times in our previous reading groups. A very important knowledge point from the convex optimization. And of course, we can find this, find the paper online if you are interested. Yeah. And another interesting application to talk about is the progressive GAN, which is so the idea is that for those images, we begin with a very low resolution image and a very shallow network. And when we say it's well trained, we then add more layers and train the new layers. Add new layers to the to the network and make the figures into a higher resolution and train the new layers, and then again and again. It's like we are trying to add more layers and train the new layers and make the images into higher resolution. It's this kind of a training pipeline. And this is an interesting effort that bypasses the size bottleneck by not having to train the whole network at once. It's like every time we only need to train the new layers. And also there's a paper called a big gun, which means that it's all their efforts is on how to scale up a gun. It's because the generative adversarial network generally benefit dramatically from scaling up. So they are trying their best to scale up the guns. First, they have more parameters, and then they have larger batch size to avoid overfitting. And after that, they try to simplify the architecture, so that they try to improve the scalability. And another interesting and somewhat related application of the generative network is what we call the normalization flow. So the basic concept of the normalization flow is to transfer a very simple distribution into something that is more complex, and more complex always means more powerful. And so that we are trying to transfer something that's way too simple into something that's complex enough. And the illustration figure is coming from Professor Xing's lecture slides. And he also mentioned in his lecture that that some existing libraries do this kind of transformation all the time. Like, for example, we can transfer, we can finally generate a Gaussian distribution by starting from a uniform distribution and transform again. Yeah. And so a single transformation looks like this. A single transformation starting from a distribution z, and we get the transformation function f, generate x equals to f z. To make the inference possible, we want it to be, the functions to be invertible. And also to compute the density of x, like the x is the transformed version of the z, we finally have this. Yeah, so we have this expression which involves some Jacobian determinant. That's what we call it here. There are existing tricks to make Jacobian determinant easier to compute. Like, for example, making this a triangular matrix, putting limits on it. And if we have multiple steps of transformation, instead of just transforming z into x, we can have x being the final output of z. Z could have k transformations concatenated together, and the finally the density is like this. And then we maximize the log likelihood when we maximize the likelihood, we try to compute this expression. And again, we apply the same regularization, the same restrictions to make the computation of the Jacobian determinant easier. And one example of the normalization flow is a model called GLOW. GLOW, it's like, and also we can find it online. It's a paper published in 2018. It's like one step of the flow in the GLOW model go past these layers, and activation, normalization, and there's an invertible 1x1 convolutional layer, and there's an affine coupling layer. And this could be regarded as small building blocks of potentially large architectures. It's not as powerful as GAN, but the good side is that this model is cheap and it's easy to compute. And the last topic that we're going to briefly cover is some efforts of integrating domain knowledge into into the generative models, deep generative models. And so first, the motivation here is that the deep learning has some disadvantages by itself. As I think all of us have experienced this, it's like we rely heavily on the massive amount of labeled data, and it's normally uninterpretable, and it's generally hard to encode the human intention and domain knowledge properly. And in the human learning, we have different ways of learning. We like in one of the way that we learn is to learn from examples, which is similar to deep learning ideas. But we also have other ways of learning, like we can learn from abstract knowledge, definitions, logical rules, and then directly apply that. And so in general, we can write the idea of how to integrate domain knowledge into deep learning like this. It's like we have a statistical model X that's like generated from like P theta X in general. It could be conditional model where we omitted some conditions, for example, a Z. Could be a generative model, and also could be a discriminated model. We don't care. We just write it this way. And we also write a constraint function, F5 X, whose output is a real number. It's like this constraint function does not generate some like distribution or so. It's generating a score. And this score means that the higher it is, the better quality X will be with respect to some of the prior knowledge. And some useful examples, like or more, maybe motivation examples on why we need to integrate the domain knowledge. Like for example, if it's an image example, it's like if we don't have some true target of the human gesture, then it's could be generating some very scary image where we find the whole body somewhat twisted or somewhat like yeah, that doesn't look like a real human being. And but if we have some prior knowledge, like how human will look like in some of those gestures, and then it could become much better. And another example could come from an NLP. It's like if we want to do the sentiment classification of a sentence like this. For example, this was a terrific movie, but the director could have done better. if we are human beings, we understand this like if because we know the grammar rules. Like when we see A but B, then B is the focus. So we know that the director could have done better. So this is not that positive a sentence. And this could help enhance the performance of the classifier. And here, integrating domain knowledge into deep learning, one way is to impose the constraint um, um, to maximize this, like the expectation of this f, which is the domain knowledge, and over p theta, which is the what we generated. Well, but this is this equation, like where L theta was like the original loss, and the second part becomes the 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 domain knowledge loss. And we can do this in theory, but it will be hard to compute in general. And this time here, a lot of text. It's like how to say? So this involves a very an explanation that comes lately on why we need the log derivative trick all the time. It's because we are trying to and it's not like why we are trying to use the log derivative trick. It's like why we suffer from the high variance all the time. It's because when we compute this, we use the log derivative trick, and in the end there becomes a log probability itself, and of course with something else, and that term, I think I will point it out in the previous slides, and that term will easily exploded. It has very high variance and it's extremely unstable. Yeah, you can go back to the wake sleep phase to have a second look on it. So in general, like coming back to this part, it means that it's difficult, generally difficult to compute this part directly. We are adding too much challenge to the computation of this problem. And so a variational approximation to ace the computation is, again, it's like kind of similar with the idea of the variational inference. Is just we just add another thing. It's called a Q, right? It's like we want Q and P to be similar to each other, and we also want to estimate f phi on Q. It and then it introduces some variational distribution Q, and it's like the objective will finally become like this, a combination where alpha is just a parameter to have a balance between their weights. And also, once again, we can apply EM algorithm, EM style algorithm to compute this. And the E step could be like this. We can compute a Q star. And this approach is known as a soft constraint. It's because the higher value of the oh wait, yeah, it's like okay, I think it's because the higher value of the lambda phi and the higher probability under Q. Yeah, so it's generally a soft constraint. It's which means that it's not hard. It allows some soft adaptation. Yeah. And how to say? Yeah. And also, let's consider a supervised learning and an input target space with the first order logic R and lambda, where R means means the rules, and lambda is the R, the yeah, lambda R, the confidence level of the rules. And here, similarly, we have the E step result of lambda R, which means that it's lambda. It's like the weighted importance of those rules, and it's like taking all the rules into consideration. And yeah, and it's like there's a similar efforts were made by Hinton on knowledge distillation, and this logic rule regularization could be found in this paper. ACL 16. And knowledge distillation is also on integrating some domain knowledge into the probably generative models, but the framework is generally a little bit different. So first we have a student network that's just ordinarily a network, a student network, and it's typically difficult to learn directly, and typically contain only labeled data. Sorry for the sentence. It's like contains only labeled data. This text is redundant. Okay, and we have teacher network, Q star, which is an auxiliary, and it, like it's an auxiliary network, and could be a variational approximation, and this is designed almost always designed to be an ensemble network. It takes labeled data, but could also take unlabeled data as well. And we have some soft prediction from the teacher network. Some soft prediction means that it's not only 0 or 1 from the teacher network. And like it's like train the teachers in one step, train the students to imitate the output of the teacher network in another step. Well, eventually get student closer to some of the teachers, or like one of the teacher, or the average of the teachers. And this and related papers are listed here. And the teacher network is rule regularized. It's like where the rule goes into the teacher's side. And recall that we have this equation to calculate the P star, and the results from the teacher networks, it is soft, and including both P theta and the logic rule constraints. And there is of course some ground truth labels, because we've mentioned that the student network learn from labeled data. And so the student output is sigma x. And so there is a so this so the soft result coming from the teacher network is this S soft here, and the hard one, the hard labels are here, the Y, and it's like the student learn from both the ground truths and from the teacher's soft result with the rules considered. And so this is the final laws. Yeah.
So can you give us example like how we can define this RL y given x?
Mm, uh,
So we probably can generate some rules. For example, if we consider whether a person is going to purchase some product, right? So we can say, oh, this if the person's age is in some range and the profession is something, then most likely this person is going to purchase that product. So then we can generate a rule. But then how we can assign score based on that rule?
I think the rules are not generated in the examples that we are talking about. So it's most likely that just how to say it's just like we have some existing rules,
Mm-hmm.
and we
We can
also
compute it, but we need to plug in and to generate some score, right? So
yeah.
we needed to given any x y pair, we should be able to judge whether this data point is consistent with that rule L. And I guess this RL function will give us that consistent score, right?
Yes, and also timed with the lambda L, which is the confidence level of that rule.
It is similar to, I mean, the form is similar to this Markov logic network. But in Markov logic network, usually it's like a hard rule, which means that we plug in this x and y, and we want to check whether to satisfy the rule. If it's a yes, then it's going to be 1, otherwise it's going to be 0. So for this RL function here, is it soft or it's more like also a hard version?
I think from the design level, it doesn't matter if it's hard or soft. But
So it's like
yeah,
up
seems
to
to me
ourselves.
it's
Okay.
soft. Yeah,
So for example, we can use probabilistic soft logic.
yeah,
Then we can get a soft value. Okay.
yes. Um, okay, and well, actually, this is how to say some more to say about it. It's like there are okay, so yeah, as Professor Sun just mentioned, it's like what we've talked about here is pretty limited. It's just a very general and like very brief idea on what could be in this world of of inserting the domain knowledge into the deep neural network. And there are, of course, a lot more to do about it. For example, people could work on having better network structures for a teacher-student network frame. Yeah, if we stick on the knowledge distillation idea. And of course, there are ways of having better rules and also learn the confidence value of each rule better. And there is a related paper on this, e.g. Kai 16. And also more generally, we can have we can like because this is some problem that we avoided talking about in this lecture because it's not that related to the main thread. It's like how we can learn to how we can learn the parameter of those logic rule constraints. And there are also papers about this, like for example this one from year 18. And teachers can reach beyond the scope of logic rules. Yeah, this is also an interesting aspect to view it. It's like teachers are not necessarily only responsible for taking care of the logical rules. And in theory, it's possible to make the reward function of a reinforcement learning as a type of teaching function. The framework could be viewed that way. And so that from this perspective, we can regard the reinforcement learning an instance of knowledge-driven machine learning. And, and sure, there are already some existing ideas on this. We can, a recommended keyword to search for is variational reinforcement learning. Yeah, and here comes to the end, to the conclusion on mostly the second half of the work. It's like there are some very interesting tricks, very interesting ideas on the variations of generative adversarial networks, and such as W-GAN, progressive GAN, big GAN, and and also like some very interesting thing about the normalization flow, which we just briefly touched it, but it's said to be much more how to say, it's like affordable, much more affordable than the generative adversarial nets. And integrating domain knowledge into deep learning, there's also a lot more to do, and also could have some like could integrate the domain knowledge into generating better samples. And that's all for today. If, uh, if there's any question. Oh, and by the way, I will correct those the glitches in the slides after the meeting is over by the end of the day. Mm. Is there any question?
I'm good. Thank you.
Thank you so much.
By the way, professors, do we still have the reading group for next week?
Yeah, I'm okay either way. So do you have exams or like busy with
by the way, I think we can stop recording now if it's still recorded.